All right, so with our knowledge then of how omega and A can relate to each other, we can now figure out the maximum velocity and also the velocity is a function of time and the acceleration is a function of time for a system that is experiencing simple harmonic motion. So we have these three expressions from before. And notice that all three of them can be written as functions of time, but the acceleration can also be written as a function of x. So it might be nice if we get the velocity also written as a function of x, so that if we didn't need to solve for the time, we could just know what the x value is and plug that in to get an expression for the velocity. Before I do that, though, let's look at what Vmax would be for this particular problem, where omega is 10 radians per second from the last example, and our maximum amplitude of vibration, let's say for this problem, is 2 meters. Well, Vmax then would be plus or minus omega A. Okay, and so here I'm taking the magnitude of Vmax because it would be minus on its way in. When it's moving this way, it would be minus omega A equals Vmax. But then it reaches this point and then moves back out again. So when it's on its way back out, Vmax would be plus omega A. But in either case, the magnitude of Vmax would be 10 radians per second times 2 meters, and that would give us 20 meters per second. The maximum value of the acceleration, and by the way, we know that this is true, that it has to be omega A, because the biggest value that the sine function can get to is 1. Okay, and so it can't get any bigger than 1. So therefore, V has to be V max when the sine of omega t is equal to plus or minus 1. Okay, and similarly for the acceleration, the A max would be minus omega squared A. So for this problem then, omega again is 10 radians per second, so it would be 10 radians per second squared times 2 meters. So it would be 100 times 2, so it would be 200 meters per second squared, where that would be roughly 20 times the acceleration due to gravity. So when it was at its maximum extent out here, the acceleration A would be minus 200 meters per second squared. And when it's at its point of maximum compression here, at this distance, x equals a away, then the acceleration would be plus 200 meters per second squared. And so this would be important then if the device that you had that was vibrating was an instrument package that could only withstand, say, 5g's acceleration, and you were giving it 20g, then that would tell you that you would have to change your design in some way to keep the acceleration below the max value that it could handle without being destroyed. Okay? And so that's the way then that we can deal with x, v, and a if we write it as a function of time. But we can also write it as a function of displacement too. And we can see how that would work on the upper screen here. If we start out with an initial velocity that, let's say, is equal to 0 when we're at our maximum extent, then at each point in the path, the total energy is going to be a combination of the kinetic and the potential. So this is x equals 0, and this is x equals a out here. And we release this from rest with an initial velocity that's equal to 0. Then this gives us the total energy is equal to 1/2 k a squared plus 1/2 mv squared. But the velocity is 0 at the maximum point, so all of the energy is potential. But by the time that we get to here, all of the energy will be kinetic. So at that point, because the maximum velocity occurs when all the potential energy has turned into kinetic, you can say at this point we would have a velocity such that the total energy would be 1/2 mv squared. And so at any other given point along the way, that's a combination of kinetic and potential. Let's say here, so this is x, but x isn't equal to a. We could call this distance here a, but we let this thing go, and now it's at some point x away. Then here, the energy will be a combination of the kinetic, 1/2 mv squared, plus 1/2 kx squared. But we also know that the maximum energy of the system occurs when it's all potential. So we can rewrite the total energy in terms of the maximum amplitude. So that this can be written 1/2 Ka squared equals 1/2 mv squared plus 1/2 kx squared. And this allows us to solve for the velocity as a function of x. Okay, so I'll do that over on the left-hand board. So we can compare that result to the value that we get here for the velocity as a function of t. So we can rewrite then the velocity v as equaling the square root of k over m times the square root of a squared minus x squared. Okay, so all I've done here then is I've taken the 1/2 kx squared, I brought it over to the left, and I factored out the 1/2 k. The 1/2s cancel out all the way through, and then I've divided through by m. So there we have k over m times a squared minus x squared, and I take the square root of that. That gives us the square root of k over m times the square root of a squared minus x squared. But we know from before that omega is the square root of k over m. And this should be plus or minus, because when you take the square root of both sides of an equation, you get a plus or minus root. And so a lot of times we don't use the minus solution, but in this case we will. So just doing that little bit of algebra gives us this expression for the velocity. Now does this reduce to this value for the velocity when v equals v max? Well, yeah, because when v equals v max here, the sine omega t has to equal plus or minus 1. So v is omega a. Here, the velocity has to be a maximum when x equals 0. So that means v is equal to plus or minus omega times the square root of a squared, or plus or minus omega a. Okay, so these two agree with each other when we're dealing with the maximum possible velocity that the system can have. So here we've got the velocity as a function of displacement. We also have the acceleration can be written as minus omega squared x. So the acceleration can also be written as a function of displacement. Or we can write all three of them in terms of their time dependence. And they're both equivalent, but it depends on which kind of problem we're trying to solve. One in which we know the initial x values, or one in which we need to... This could be kind of cumbersome, though, if you're trying to say, find v as a function of x, and you have to find the time from the inverse sine function, and then plug in the cosine of the inverse sine. That is a little trickier than just writing out a single equation and solving for the velocity as a function of x. So that's why this kind of a problem would be preferred. That form for the solution would be preferred for that kind of a problem. All right, so let's do an example. Let's say that we have a mass, and from before, we can set the mass equal to 100 grams and the K value again equal to 10 newtons per meter, so that the omega value is 10 radians per second, as we did before. And then, let's say that this distance here is a, but we let x go to a over 2. So in other words, we release this thing from rest until it reaches this point. Let's find the velocity when x equals a over 2. So in other words, we're halfway back. Okay, so you let the thing go from its maximum displacement until it's at the halfway point, and then we try to find what the velocity is at this point. And then let's compare that to Vmax. Now we know what Vmax is. Vmax is going to be equal to, from over here, plus or minus omega A. So for this problem, let's say that A is equal to 1 meter, so that x then would be equal to 1/2 meter at the halfway point. Then Vmax would be omega A, that would be 10 radians per second times 1 meter, or 10 meters per second. And then V at x equals A over 2 would be plus or minus omega times the square root of a squared minus a over 2 squared. Because here, at this point, where we want to know what the velocity is v, this is v of a over 2. That's the velocity as a function of x at x equals a over 2. We have that expression. So this is going to be omega times the square root of 3a squared over 4, or that is going to be square root of 3 over 2 omega a, or 0.866 times Vmax. Okay, so the percentage then of the maximum velocity, when it's at its halfway point, it's going to be already at 86% of the maximum velocity it has when it's at x equals 0. Okay, so why is that? Well, because most of the force was gotten through this half of the motion. Okay, because the force is larger, and the force is getting ever smaller as we go through that second half of the motion. So if we wanted to write this in terms of Vmax, and Vmax was 10 meters per second, then the velocity would be equal to 8.66 meters per second. So that would be our velocity when x equals a over 2. Okay, so that's one question that we can ask. Another one that we could ask is, what percentage of the energy is kinetic versus what percentage is potential at x equals a over 2? Okay, well, we know that most of the maximum velocity is in the form of, it's going to be in the form of kinetic energy. So I might guess that I have more kinetic than potential. But we have to be careful when we're doing this. So remember, kinetic energy is 1/2 mv squared, but potential energy is 1/2 kx squared. And so I've asked this question before on a number of different exams. And if you see how to do the problem, it comes out pretty quickly. But if you don't see how to do it, you can end up with a whole page worth of chicken scratches and never even get close to getting the right answer. So what I would want to do here is compare, this is my strategy for this problem. One half kx squared to the total energy which can be written as 1/2 ka squared. If we do it that way, knowing that the total energy is 1/2 ka squared, that's when it's all potential that's out at this point here where x equals a, then we can see immediately that since x is equal to a over 2, the potential energy is going to be equal to 1/2 k times a over 2 squared, where that will be 1/4 times 1/2 ka squared. And so that would equal 1/4 of E total. So therefore, the potential energy is 1/4 of the maximum energy of the system, and therefore the potential energy is 25%. Now, if the potential energy is 25%, then the kinetic energy must be the rest, or 75%. And so what's the ratio then of these two? Well, it would be in a ratio of 3 to 1. Okay? And so you'd have 3 times as much kinetic as you have potential. The potential would take up 1/4 of the total energy. The kinetic would take up 3/4 of the total energy.